One of the consequences of the second law, and probably the most difficult concept to define or to understand in thermodynamics, is entropy. Entropy is a new concept that was introduced in thermodynamics in order to measure the second law or the effects of the second law. And I'm going to explain a little bit of this, but I want you to understand that this is a convenient function, as enthalpy, for instance, was a convenient function, and it is very difficult to actually understand its physical concept. This function is defined, for instance, in a differential way as the differential of the heat with respect to the temperature in a reversible process. And it's a state function, so it means that, for instance, if I have a graph, right, and I start in this point and I end up in this point, if I go, for instance, no matter which path, the change in entropy is going to be such that this is going to be S2 minus S1. And since we are, for instance, stating that the differential of entropy equals the differential of heat with respect to temperature, and it doesn't matter really the path, well, the path could be a reversible path and we will be fine. So at the very end, the change in entropy is going to be the integral of the differential of heat with respect to temperature. If the process is, for instance, an isothermal process, that no matter what we do, the temperature of the system will not change, then delta S is going to be equal to, T can go out from the integral, and the integral of the differential of heat is the heat over the temperature. I suggested previously that the second law is going to determine the direction of the transfer of energy. So what does that mean in terms of entropy? Imagine you have a low temperature system and then a high temperature system, right? And it is very straightforward to understand that the heat is going to be transferred from the higher temperature system to the lower temperature system, right? And it's not so very convenient to state, or you don't actually see nature the other way around. And the amount of heat that is going to be transmitted from the high temperature source to the low temperature system is going to be the same as the one that is received by the low temperature system. So the heat is the same. And if we want to determine, for instance, the entropy, well, we can actually understand that the entropy, the change in entropy that is going to be, for instance, received, it's going to be positive because it receives heat with respect to the lower temperature, the temperature of the lower system, right? That's the entropy. While, for instance, the delta S is going to be negative, right? So this is going to be the entropy of the higher temperature system. It's going to be negative, it's going to be losing, for instance, entropy, or having a negative entropy. If we do a balance of the whole system and we analyze the entropy for the whole system, we can actually understand that, for instance, this could happen, right? And in this sense, this guy is higher than, for instance, this guy, right? So this is going to be, for instance, larger than 0. It's going to be a positive value. And then we understand that in that case the transfer is going to be natural, right? So the entropy will state, for instance, in a set of systems where energy is being transferred, the transfer will occur in a spontaneous way if the change in entropy for the whole set of systems, the addition of both entropies, is larger than zero or is a positive value, which will actually state that entropy is always being generated. Second law will state, and this had a lot of implications that I will not discuss here, but it will state that the process will have the direction where the entropy is going to be generated.